Hello friends. Heartily welcome to this session. In this session, we will discuss the previous IES problems and its solutions, and the topic is network elements, and we will discuss the problems asked in 1992 to 2013 IES. So let's start our discussion. The first question on the screen here is the number of turns of a coil having a time constant tau are doubled. That means the time constant will be dash. That means, so here L is proportional to N square base, as we know this from the formulas, and here we have L by R. Okay, so from this what we need to find is that time constant when the number of turns of a coil are doubled. As the number of turns of a coil are doubled, whatever the time constant is also doubled here. Next, in the circuit shown, V1 and I1 will be. Here the voltage across this 1 ohm resistance is 5 volts here, and this 1 amp current has no effect here. That means this is not having any effect, so I1 is nothing but V1 by 1 here. So this is 5 amps here. Next question. Third question. The current having a waveform as shown in the figure is in resistance of 10 ohms. The average power will be. So P average is equal to IRMS square into R plus E is equal to. So IRMS for this waveform is, we have calculated these values in my previous videos. So from that, so 10 by root 3 whole square into R. This is the 10 by 3 watts here. Next problem. And this is the answer. A 24 volt battery of a internal resistance R is equal to 4 ohms is connected to a variable resistance R. The rate of heat dissipated in the resistor is maximum when the current drawn from the battery is I. The current drawn from the battery will be I by 2 when R is equal to. So here we have a 24 volts battery and its internal resistance is 4 ohms, which is connected to a variable resistance R here. Okay, the rate of heat dissipated is maximum when the current drawn from the battery is I. So when I is the current flowing, then we need to find the current value. So from maximum power transfer theorem, to produce a maximum power, RS should be equal to RL. That means the source resistance should be equal to load resistance. Okay, so from this R is going to be 4 ohms here. So now I is nothing but from the circuit we will calculate 3 amps, and now the condition asked is the current drawn from the battery will be I by 2. So now the current is decreased to half value. At that particular point, what is the R value? So what we will do is we will again apply KVL here. So minus 24 plus 4 into I1 plus R into I is equal to 0. Okay, so already we know that I value. I is nothing but 1.5 here. So from this I is equal to 24 divided by 4 plus R. I is nothing but 3 by 2. If we substitute this equation, we will get R is equal to 12 ohms here. Next, our fifth question here. So in the fifth question in the figure, if we connect a source of 2 volts okay, so in a circuit shown figure, if we connect a source of 2 volts with the internal resistance of 1 ohm at A dash A terminals here with the positive terminal A dash at A dash, then the current through the R will be. So here by using the nodal analysis I am going to solve the equations. At nodal analysis, as we know that the current entering at the node is nothing but indicated with negative sign here. So minus 1 amps plus V1 by 1 V1 plus V1 minus V2 divided by 1, okay, is equal to 0. This is the first node equation. At node 2 here, V2 minus V1 by 1 plus V2 by R, that is 2, V2 by 2 plus V2, and here we have minus 1, so plus sign. Okay, so V2 minus 2 divided by 1. So by solving this equation, we will get the answer as 0.625 amps. So this is the answer here. Okay. Next, sixth problem. In this problem, in the circuit shown the value of I we need to find here. So here what we will do is we will form a source transformation technique. In source transformation technique, a current source in parallel with the resistance can be represented as a voltage source in series with the resistance. So here V is equal to I into R. So V is equal to I into R here. So from this, what is the current here? So current is 10, resistance is 4. So this is equal to 40 volts and series the resistance. So series, and here 28 is a resistance, and the current source in parallel with the resistance can be represented as a voltage source in series with the resistance. So here we have minus sign, plus sign here. Okay, reverse direction, current moving in the opposite direction. So like this. Okay, by solving this we will get I is equal to 2 amps by using KVL. Next, seventh problem. When all the resistances in the circuit of 1 ohm each, the equivalent resistance across the point A and B will be. So I have redrawn the circuit in this shape here. So between A and B we need to find here. Okay, suppose before going to solve this type of problems, just check whether the bridge is balanced or not. So bridge is balanced means the opposite resistances 1 into 1 is equal to 1 into 1. Okay, the bridge is balanced. When the bridge is balanced here, this resistance has no effect. So that the R equivalent will be 0.5 ohm. 5 ohms here. Or you can solve this problem by converting this branch into delta. So star to delta connected network. We can also solve this problem like that. Next, a battery is connected to a resistance causing a current of 0.5 amps in the circuit. The current drops to 0.4 amps when the additional resistance of 5 ohms is connected in series. The current will drop to 0.2 amps when the resistance is. So here what they are asking is, here we have a network, a battery which is connected to a resistance. We don't know the resistance value, but the current flowing is 0.5 amps. So if you draw like this, so from this a battery and resistance, the current is 0.5. So V is from Ohm's law, V is equal to I into R. So that is V is equal to 0.5 into R. This is the first condition. And the current drops to 0.4 when additional resistance of 5 ohms. So current drop to 0.4. So this is the current here, 0.4 here, when we add a resistance of 5 ohms. So from this KVL, what we will write is, so already we know that V value. So V is equal to 0.5 into R. So 0.5 into R is equal to, from this equation, 0.4 into is a current into R plus 0.4 into 5. We will get the solution as. Next condition is, so from this we will get R is equal to 20 ohms, V is equal to 10. So previous values, that is V is equal to how much? 10 volts here, and R is equal to 20. We got these values. Now next condition is, when the current drops to 0.2 amps and additional resistance is. So already R is a resistance that is available existing in the circuit. So this is R value. So this is already pre-existing value, and this is also existing value. Now we have to add extra resistance so that the current is going to be 0.2. So by applying Ohm's law here, so minus 10 plus 0.2 into R external plus 0.2 into 20, we will get the answer as 30 ohms. Friends, next question. The current in the resistor in shown by. So for now to solve this technique, I am going to use a node analysis here. Why? Because in parallel networks, node analysis will give the much faster results. Okay. So here from this node analysis, the current always leaves the node until unless if they are specified. So V1 minus 2 divided by 1k plus V1 by V1 minus 1 by 1k plus V1 minus V2 divided by 1k. So at node 1 equation, and we solve this, we will get this equation. And V2 at node 2. So node 2 here, and this is for node 1 here. At V2 here, we will get V2 minus V1 divided by 1k. V2 minus V1 divided by 1k plus the current is entering minus sign here, minus plus V2 divided by 1k is equal to 0. By solving these two equations, you will get the answer as 0.2 amps. Next question. The circuit shown is a linear time invariant one, and the sources are ideal. Choose from the answers given below the value of voltage and current through the 1 ohm resistance. So this type of problem we have done earlier, that once the 5 voltage is a voltage across this resistance, the current is going to be I is equal to V by R, that is a 5 amps 5 volts. So this type of problem we have seen earlier. Next question. The equivalent capacitance across AB will be. Okay, here. So this is a question asked here. This is a circuit diagram. So here we need to find the capacitance between A and B. Okay, so I will reconstruct this network into a bridge form so that I can check whether the bridge configuration is balanced or not. Okay, so all the units are in microfarads here, and from this we can get that the bridge is balanced here. Why? Because 0.1 into 0.1 is equal to 0.1 into 0.1. So bridge is balanced here. Okay, this value. Okay, next, the equivalent capacitance. When the two capacitors are in series, they are having a property of division here. That means 0.1 and 0.1. That is 0.1 by 2 is equivalent, and 0.1 and 0.1 they are in series. That is 0.1 by 2. So we have discussed this type of series and parallel connections of capacitance in my previous lectures. Okay, you can watch it. So from that, equivalent capacitance will be 0.1 in microfarads here. Okay, answer is 0.1 microfarads. Next, 12th question. The Kirchhoff laws is valid for an AC circuit containing RLC, and the reason is the sum of the RMS currents at any junction of the circuit is always 0. So reason is wrong here. KCL is valid for RLC. So the answer is A. That is, so both A and R are true, but not sorry. A is true, but R is false. Okay. So the answer is A is true, but R is false. Next question, 13th one. In the circuit shown in figure, the voltage across 2 ohm resistance is going to be. So simply by applying the nodal analysis, here current entering is minus 6 plus V1 by 1 plus V1 minus V2 by 2. So node 1. And node 2 is V2 minus V1 by 2. And so before going to solve this, V2 is nothing but 3 volts directly. So by substituting this, we will get the answer as 2 volts. Next, if a capacitor is energized by a symmetrical square wave current source, the steady state voltage across the capacitor will be. So here we have a capacitor is energized by a square wave current source here. Okay, we know that I is equal to C into dV by dt, Vc is equal to integration of 1 by C into integration of I into dt. Okay, so integration of square wave will gives rise to ramp signal or triangular signal. The Vc capacitance voltage will be like this. Okay, and the answer will be triangular wave or ramp wave. Here, 15th question. 4 network elements, 4 networks are shown in figure 1, 2, 3, 4 here, and the question is, okay, so out of these networks which are having equivalents, so here the voltage across these elements, so V is equal to I into R, V is equal to d by dt, so V is equal to 1 by C into integration of dt, and the same equations, voltage equations are valid for this case and valid for this case and valid for this case also. But that means in the 4 given networks, all the are having the 4 networks are equivalent because they are having same voltage equations. Next, 16th question. The number of 2 microfarads 400 volts capacitors are needed to be to obtain a capacitance value of 1.5 microfarads rated at 600 volts. So friends, here one capacitor is having 2 microfarads and 400 volts. How many capacitors I need to connect in series so that I will get 1600? So they are, so 4 into 4 means 1600 volts, right? But when the capacitors are in series, they will reduce its value, just as in parallel connection. So 2, 2, 2. So 2 by 4. Okay, 1 by 2. 0. microfarads is the equivalent one. But I want to get 1.5. So I will add 3 branches. So total will be 12 here. 17th question. A connected planar network has 4 nodes and 5 elements. The number of meshes in the dual network. So when we are converting dual from this network to dual network, okay. So here I will take, so B and D connected to node 3 here, and C and E connected to node here. So C and E connected to node here, and the number of meshes is going to be 3 here in this case. Next one, the number of current I flowing in 1 ohm resistor in the circuit shown in the given figure is going to be. So here, if voltage source is having parallel with the current source here, okay, anything parallel with the voltage source is redundant. That means we can neglect it. Okay, so the current source in parallel with the voltage source can be neglected. So the current source has a no effect, and the current is going to be I is nothing but V by R, that is 5 amps here. 19th one. In the circuit shown in figure, the current I flowing through the RL, load resistance here. Okay, so by using nodal analysis we can follow. So V1, okay, always assume that the V1 is higher potential compared to other voltages on the network. So V1 minus 420 divided by 120 plus V1 minus 420 divided by 60 plus V1 divided by 30 is equal to 0. So if you solve this equation, we will get the answer as 6 amps. And next one, a simple equivalent circuit of 2 terminal network shown in figure. So this is we need to find the equivalent. As we discussed earlier, that a voltage source in parallel with any current source is can be represented as a voltage source only. So the current source is going to be redundant here. That means a voltage source instead the resistance. So this is the equivalent network. Next one. A voltage source with an internal resistance Rs supplies power to a load RL, that the power delivered to the load with RL varies. So here a voltage source with internal resistance Rs here, which is connected to a load RL here. So we need to find what is the power delivered to the load varies with respect to RL here. That means if the RL varies, how the power is going to be behave. So if you in order to find this power dissipated in the resistance is going to be P is equal to I square R into RL. I is nothing but from this equation we can write the KVL here. So from this we can write I. So I is nothing but V minus Vs plus Rs into I plus RL. So I is nothing but Vs divided by Rs plus RL here. So P is equal to I square. P is equal to I square into RL. No? So I is nothing but Vs square by Rs plus RL whole square into RL here. Okay. And maximum power occurs, as we know that from the maximum power transfer theorem. Maximum power transfer theorem, it says that source resistance should be equal to load resistance. Okay, at that time we will get maximum power transfer here. But here the thing is here we have to identify the wave shape here. So in order to identify the wave shape, so just P is equal to V square by Rs plus RL whole square into RL here. So as a load resistance is 0, what will happen? P is equal to 0. This is the first equation. As the load resistance is equal to source resistance, okay, so P max is equal to V square by 4 RL, and as RL is a maximum value, say not infinity, maximum value, as it maximum value, what you will get is, so V square divided by RL is much more compared to RS, so that we can neglect the RS here. So we will neglect the RS here, approximately RL square into RL here. Okay, so that what we will get in V square by RL. So as is approximately equal to infinity, that means P is going to be 0. Okay, so P is equal to 0. So from these characteristics we can say that, so C is the graph which represents the variation of load resistance with respect to P. Another important thing is the load resistance should equal to the source resistance. Okay, so here this one is a variable and this one is a constant. Next one, an inductor with an inductance L and the current I naught as shown in figure. So as we know that from the one of the forms of Ohm's law, we derived that I of t is equal to 1 by L into integration from minus infinity to t into V into dt. Okay, so from this we will derive that initial current flowing in the inductor is I naught by S plus V of S by Ls here. So by using this Laplace transformation here. Okay, and from this the equivalent circuit will be D here. Next, a signal is described with S of t is equal to R into t minus A minus R of t minus B. A is less than B, where R of t is a unit ramp function starting at t is equal to 0. The signal represented here. So S of t is equal to R of t minus A minus R of t minus B here. So first I am starting the signal A here. So t minus A is nothing but delayed here. So R of t minus A is moving like this, is a ramp signal here, starting at this point, and R of t minus B starting at this point here, at point B. Okay, so when we just subtract this, we will get this value as, okay, this is the wave shape or signal represented. Okay, the answer will be here is, so C here. Next, a unit impulse input to a linear time the unit impulse input to a linear network has a response R of t, and a unit step input to the same network has a response S of t. The response R of t is, so here we have a linear network, so for which first we have given a unit impulse response, unit impulse as an input, and we will get the response as R of t. So next time what we have done is, we have given a step input to this response to the system, linear time system, and we are getting the output as a delta of t. Okay, so S of t, the relationship between S of t and R of t. Okay, the relationship is given by, so S of t is nothing but unit step response is equal to differentiation of ramp response, impulse response. So impulse response, sorry. Okay, the answer is yes. A. Next, 25th problem. So this is the problem. The current waveform in the pure resistor of 10 ohms is shown in the figure. Power dissipated in the resistor is going to be, so here 9 is a magnitude here. So from this I of t is nothing but 3 into t. From this equation I value we get, and this and it is a interval 0 less than t less than 3 here. Okay, IRMS square is equal to 1 by time period, that is 1 by 3, integrating from 0 to 3 and 3t square into dt here. So from this we will get 27. Power dissipation is equal to average power is equal to RMS square into R, 270 watts. Now consider the following statement. The unit impulse delta of t is mathematically defined as, okay, so generally how we'll define it is, unit impulse is having area of unity. Area under the curve is going to be unity always. So here it is going to be valid only for when t is less than 0 or equal to 0 and t2 is greater than 0. So limits are t1 here and t2 here. So here we have t1 and t2 at these particular points here. Okay, so t1 should be less than 0 and t2 should be greater than 0 or equal to 0. So here under the curve is integration t1 to t2, delta of t is equal to 1. So from this case, delta of t is equal to 0 when t is not equal. So this is the first statement is correct. And from this, integration starts from minus infinity to plus infinity here. So from this, the answer is going to be 3 here. Next, two coupled coils in series have an equivalent inductance of 16 or 8 millihenry. That means they are asking for this is for AD in series AD and this is series opposing. So this value, okay, depending upon the interconnections. Okay, right. And then the mutual inductance M will be, so L equal is equal to L1 plus L2 plus 2M for, this is for series AD and this is for series opposing. Okay, from these two equations we will get the M as 2 millihenry. Next, here two coupled coils L1 L2 is equal to 0.6 Henry and having a coupling coefficient of K is equal to 0.8. Then turns ratio will be, as we discussed earlier, that L is proportional to N square. Okay, N is proportional to N square here. So from this, L1 L2 is equal to N1 square by N2 square. So from this, N1 by N2 is equal to square root of L1 by L2. So L1 L2 are same values. That means it will have a turns ratio of 1. Next, the coils having self inductance 10 millihenry and 15 millihenry have an effective inductance of 40 millihenries when they are connected in series AD. What will be the equivalent inductance if they are connected in series opposing? Just before you see in the formula, L equivalent is equal to L1 plus L2 plus 2M for series AD. L equivalent is equal to L1 plus L2 minus 2M. So okay, if we substitute this, we will get the answer as 10 millihenry here, right? And next question, that is one. Next question here, that is one. Two condensers, that is capacitors of 20 microfarads and 40 microfarads capacitors are connected in series across a 90 volt supply. After here you have seen 90 volt supply here, right? After charging, they are removed and from the supply and they are connected in parallel with the positive terminals connected together, and similarly negative terminals are connected together. Then what the voltage across the then will be. So first case is we have two capacitors or condensers which are connected to in series and the voltage is going to be 90 volts here. And next case is when they are removed and connected in parallel with the positive signs upper and negative signs lower here, then what will be the voltage here? Okay, so here from this voltage division rule of capacitances, from this we can calculate V1 is equal to 90 into opposite capacitance. Okay, that is 40. So here we are going to find V1. Okay, so here we are going to find V1 divided by 60 is equal to 60 volts here. Okay, in series network current is same, so the charge is also same. So Q2 is equal to, or Q1 is equal to C1 into V1. So what is the C1 value? That is the capacitance. Suppose it's C1 20 microfarads, 20 to the power minus 6 into V1 is nothing but 60 volts. So we can also find V2 also. So V2 is nothing but 90 into 60 divided by 40. Okay, so what is 60 here? 60 you will get. So from this 30 volts, or you can directly find from the KVL, we will get V2 is equal to 30 volts here. So Q1 Q2 is 200 microcoulombs here. When they are connected in parallel here, that means when they are connected in parallel, the charge stored in this capacitances are connected in parallel so that they will travel like this and they will added in nature. So Q total is going to be, previous case what is the value? So Q1 is 1200 microcoulombs here. So we will get 2400 microcoulombs, and C equivalent when they are in parallel, C1 plus C2 will get 60 microfarads. So Q is equal to C into V, V is equal to Q by C, will get 40 volts as a result. Next, 31. The voltage and current relationship for the network shown in figure is VI is equal to 4I minus 9. If now a resistance of R is equal to 2 ohms is connected across it, then the value of I will be. So previous cases, here we have a network here. Okay, in this network, what we have done, the voltage is there here. Okay, right. but the current is flowing in this direction here. That means previous cases the voltage is supplying the current into the network. Now what we have done is a resistance is connected here. Okay, so if you apply KCL here, this current is equal to opposite of this current here. Okay, so from this what you can write is, so here from this equation what I have done is V is equal to 4I minus 10. I have represented in the equation form like this. Next case here is, so I is flowing in this direction, and by applying KCL I will get that I is equal to minus V by 2. There is an opposite direction, so that I have considered minus V by 2. Already we know V value, so V is equal to 4I minus 2. So I is equal to, or minus I is equal to 4I minus 9 divided by 2. So from this, if we solve this equation, we will get I is equal to 1.5. Next case, in the delta equivalent value of the given star connected network is equal to, so here they have given a star connected network, we need to find the delta equivalent value in between Q and R here. So between these two terminals here, what is it QR? So from the star delta conversions we can calculate easily. That means I said QR is equal to the sum of this resistance plus the product of these two resistance divided by this one. Okay, you will get this answer. Next case, 33 problem here. Consider two circuits 1 and 2 as shown in the figure. Find the values of A1 and A2 and give the result. So by applying the nodal analysis here, so first V1, so V1 is superior than that of other voltage, so V1, the current flows leaves from this V1 here, so V1 minus 10 divided by 10 plus V1 by 20 plus V1 by 20 is equal to 0. So from this I will get I1 as 0.25 amps. Similarly in this circuit, again applying the same analysis, nodal analysis, so V1 by 10 plus V1 by 20 plus V1 minus 10 by 20, you will get the answer as A1 and equal to. So the solutions are going to be, the currents in the A1 and A2 are of the same value and equal to 0.25 amps, and the other options are wrong. 34th problem here. In the circuit shown below, if I1 is equal to 1.5 amps, then I2 will be. So here also I am applying nodal analysis here. Okay, so from the nodal analysis we can write that if I1 is equal to 1.5 amps, okay, so the current is entering here, I am considered as a minus sign, so minus plus V1 by 2 plus V1 minus 3 by 2, we will get the answer as 1.5. okay, I is equal to 1.5. Next, an input f of t is applied to a linear network giving a response g of t. The function f of t delayed by one time unit. If the network is in time invariant, then the response will be, the property of linear time invariant network is going to be, if you give f of t as a function, you will get a response as g of t. Then if you delay the input by 1 second, so that say time here, and the output also delayed by 1 second. Why? Because it's a linear time invariant system. That's its problem. The current shown in the given figure passes a pure inductance of 3 millihenry. The instantaneous power in watts during 0 less than t less than 2. Here friends, important thing is, here they asked for instantaneous power. Okay, so in order to solve this instantaneous power, P of t is equal to V of t into I of t for the time period they have mentioned is 0 less than t less than 2. So I of t for 0 less than t less than 2, you will get the slope of this equation as 5t into 10 power 3 amps here. Okay, and V of t is equal to pure inductor, no? So V is equal to L into dI by dt. From this you will get 15 volts here. So differentiation of t is nothing but 1. You get 15 volts. So P of t is equal to V of t into I of t. So P of t you got, I of t is you got. So 15 into 5, 7500 into 75 into thousands into time, t is a time, instantaneous period, right? So from this t we can find what is the instantaneous power at every instant here in this waveform. Okay, so t may be 2, t is equal to 4, or t is equal to 6, we will get the answers. Next, which of the following are true of the circuit as shown in the figure? So Vy of V1 of t is equal to, V of t is equal to 215 root 2 into sin 300t. Vr is equal to 100 volts, I is equal to 2 amps, L is equal to 0.25. So we have to calculate everything in detail here. So Vs RMS square is equal to Vr square plus VL square. So this is the equation. So here important thing is Vs RMS square, right? So Vrms V maximum, this is a V maximum value. So here we have So V maximum is equal to 250 into root 2. So V RMS is equal to Vm by root 2. So that 250 into root 2 divided by root 2 will get. So VRMS whole square is equal to VR square plus VL square. So from this VR is equal to 200 volts. And next thing is I. So we need to find I here. I is nothing but V by R. Why? Because in this branch whatever the current flowing here is, so VR is equal to 200 volts, and I here the same current is flowing throughout this network. So I is equal to V by R here, so that I will get 2 amps here, and VL is equal to voltage across the inductor is equal to XL into IR, that is impedance into current flowing in that inductance. So in the given problem W is given as a 300 omega t. So 300 into L is nothing but how much, we don't know value, we need to find this one value, and IR is already we know that it's a 2. Okay, so from this VL is equal to 150 divided by W 300 into IR 2 is equal to 0.25 henries. So from this which case are true? So VR is nothing, VR is wrong, I is going to be 2 and 3. So 2 and 3 are okay. So options are going to be A. Next. Two inductive coils of self-inductance L1 and L2 are magnetically coupled in series, opposing and in parallel aiding respectively. The mutual inductance between the coils is M. The equivalent inductance when two are cases separately. So when first case is when the series are opposing. So series opposing means we will write L1 plus L2 minus 2M. Minus sign will be here. So when series connection L1 plus L2 plus or minus 2M here. Plus sign for aiding, minus sign for opposing. So minus sign for opposing here. Next, L1 when parallel connections. In parallel L1 into L2 minus M square divided by L1 plus L2 plus or minus 2M. So here different cases. So here plus for opposing. Okay. So here minus for opposing. And here minus for aiding here. So the asked is parallel aiding. So parallel aiding you will get minus sign here. So this is the answer. 2. Coupling. The coupling between the two magnetically coupled coils is said to be ideal if the coefficient of coupling is going to be 1. So coefficient of coupling is given by K is equal to M divided by square root of L1 L2. Okay. If for tightly coupled or perfectly coupled, the mutual inductance is equal to square root of L1 L2 here. Or we can write this on as, so M square is equal to L1 L2. Next. For the network shown in figure A and B to be duals, it is necessary that R dash, L dash, C dash are respectively equal to. So in duality, resistance becomes conductance, inductance becomes capacitance, capacitance becomes inductance, voltage source becomes current source, and series connection becomes parallel connection, and parallel connection becomes series connection, and current source becomes voltage source. Here another important is mesh becomes node, node becomes mesh. So here I will write, so mesh becomes node, and a node becomes mesh here. According to this, here we have series connection. So Vs becomes current source here. Okay. R becomes series connection becomes parallel here. R becomes R dash. So R dash is going to be G, and L is going to be C, and C is going to be L. Okay. So from this we will get the answer will be as A. Next, in the for loop 1 of the network shown in given figure, the correct loop equations. Okay, so we have done the correct loop equations here. So here by applying the loop equation, minus V of t plus R into I of t, plus here there is a inductance, the mutual inductance between these two couples. So plus L into VL. So VL is nothing but here. So VL is equal to L into di by dt. So VL is equal to L into di1 by dt plus, I will erase this, I will write the equation again here. Okay, and this is wrong. So here minus V of t plus I1 of t into R plus here the mutual inductance. So VL is equal to L1 into d by dt, and assumed we are following the loop 1, so that the current I1 is greater than that of other currents, plus here and mutual inductance. So when the current is entering here, and also currents entering in the L2 coil. Okay, so we have mutual couplings between these two coils only, not from 1 to 3. So that is going to be plus sign. So M12 and the mutual inductance because of the current flowing in the other coil. So d by dt of I2. So the equation is A here. Next, consider the following statements in the network shown in figure. If the equivalent impedances we need to find. So in order to find the equivalent impedances here and check these conditions, these 4 conditions. So first I will do is V. So V is nothing but I1. I will write this V is equal to, so 4 plus J10. This is because of self inductance into I1 plus because of the mutual inductance of the other coil. So here the current entering at the positive terminal, here current entering leaving here. So we will get minus sign here. So minus sign here. So 4, this is a mutual inductance. So because of the current flowing in the second coil, so I2. So 4J into I2, and similarly you write the same equation. So in parallel network, parallel elements, same voltage. So V is equal to again 4 plus J10 plus mutual coupling. So we'll get minus sign here. So minus J41. So from this 1 is equal to 2, we'll get this from this I1 is equal to I2. Okay. So the effective impedance seen by the source is equal to, so V divided by, so here the current is flowing is I. This is equal to sum of the currents I1 plus I2. So I is equal to I1 plus I2. The impedance is equal to V divided by, as we know that I1 is equal to I2. So from this V by 2 into I1. Okay. So what is the V value? So V is nothing but, this is the equation. So from the one equation we know that I1 is equal to, so from this equation we know that this is the value, right? So from that we will get the answers. Okay, so I1 is equal to I2 is true here in this case, and second case is impedance is equal to Z plus J3. So 2 and 4 are correct. Next problem here is a 10 volts battery with an internal resistance of 1 ohm is connected across a non-linear load whose VI characteristics is given by 7I is equal to V square plus 2V. Then I is equal to dash. So here they have given a 10 voltage source with an internal resistance of 1 ohm and is equal to non-linear load here. The voltage across non-linear load is equal to V here, and they give the relationship 7I is equal to V square plus 2V here. So by writing the KVL inside this equation, minus 10 plus 1 into I plus V is equal to 0. So from this we will get the V value. Okay, so name it as equation number 1 and this equation number 2. So from 1 and 2 you will get the answer is as 5 or 24. The options that we are having is 5 atoms only. Next, match 1 loop concept with loop 2 list 2 junction concept. Select the correct answer using the codes given below the list. Friends, here in this case we know, we have discussed earlier that meshes is nothing but becomes node here. Outside the mesh is going to be reference node, mesh current is going to be node voltage, number of meshes is going to be number of nodes here. Okay, so from this you will get B as an answer. Next, 45th question. In this question, in the network shown in figure, the effective resistance faced by source here. The effective resistance seen by the source is going to be calculated by using R effective is equal to V by I here. Okay, by writing the KVL inside this equation, what will get? So minus V plus 4 into current flowing inside this is equal to 0 here. But before going to write the value of I4, so I4 is nothing but, so by applying KCL here, I4 is equal to 3I by 4. So by writing the KVL, what you will get? V by I is equal to 3 here. Okay. Next, the dimensions of the equation of resistance is, so R is equal to V by I, it can be written as VI divided by I square, that is equal to P divided by I square. So we will write this P in terms of SI units is equal to mass into acceleration into length divided by time into I square. So from this ml t power minus 2 L divided by T I square, that is equal to ml t square t power minus 3 into I square here, I power minus 2. Okay, next, 47th question. The number of a network consisting of n nodes and e elements is described by mesh equations or node equations. Okay, the number of mesh equations plus number of node equations equal to the number of elements. Okay, so here the statement A and the reason is true and R is supporting A. Okay, so both A and R true and R is correct explanation of A here, right? Next, the 5 elements are connected in series in a row and 4 such rows are connected in parallel to feed a current to a resistive load of 1.25 ohms. Each cell of EMF is 1.5 volts with a internal resistance of 0.2 ohms current to the load. So first what we have done is 5 cells are connected in series here. So 5 cells, if you connect 5 cells in series, so 1.25 to 5 is going to be 1.5. So 1.5 into 5 will get 7.5, and 5 resistance are in series is equivalent of 1 ohm. Such a network or such as connections is connected, 4 such a rows are connected here. Okay, 4 such a rows, 4, then 4 such a rows are connected in parallel. So such a rows are 4 here, 1 2 3 4. Okay, now now the parallel, they feeding the resistive load of 1.25 ohms here. Okay, so 1.25 ohms. Now what we want to find, what is the voltage here? Okay, so from this voltage we will find, so V is going to be 6.25 ohms, but the given question is find the current through the load. So if you know the V1 value, so from this V1 we can find, so IL is equal to V divided by R, we will get 5 amps. Next, 49 problem, right? The 4 resistances 80 ohms, 50 ohms, 25 ohms and R are connected in parallel. The current through 25 ohms, 20 ohm resistance is 4 ohms. The total current of the supply is 10 amps. The value of R is going to be, okay, so here we have connected 10 amps is total current supply, and we have 4 resistances 80 and 50, 25 are here. But what they have given hint that in 25 ohm resistance the current flowing is 4 amps here, so that I will get a voltage of 100 volts. All are connected in parallel, so all are having equal voltages. Okay, now I will apply the KCL at this node here. So at this node we will get minus 10 plus 10 by 8 plus 2 plus 4 plus IR is equal to 0. So from this IR we will get it as 22 by 8. But what we need to find, we will need to find the unknown value R here. So R is nothing but V by I. So V is nothing but 100. I value is 22 by 8. We will get it as 800 by 22 or 36.3 here in this case. Next case, a function f of t is equal to 1.1 t plus sine 3.3 t has a time period of. So in this case, omega is nothing but to omega t is equal to 2 pi. So omega 1 is equal to 1.1. Omega t is equal to omega t is equal to 2 pi. So from this, t is equal to 2 pi divided by omega, that is equal to 2 pi divided by 1.1. So this is the fundamental. But here you have other frequencies, that is third harmonic frequency. So omega 2 is equal to 3.3. So t2 is equal to 2 pi divided by 3.3. Now t2 is equal to t1 by 3 here. But the fundamental is going to be 2 pi divided by 1.1 here. Okay friends, thanks for watching my videos. If you have any questions or queries, please comment, and we will discuss the remaining problems in the next session. Thank you.